Okay, you talk in the book about this mechanism of peat formation in the
Yeah.
older lakes that is potentially a carbon sink.
Yes, when a thermokarst lake first forms, the volume of frozen sediment that thaws is increasing. And as it does, that's opening that freezer door more and more. More soil carbon thaws out and feeds the microbes. So in the initial decades to centuries of a lake existing and expanding, tremendous amounts of methane gas are coming out of the lake. But over time, if that lake doesn't drain, and by over time, I mean decades to a century or centuries, there's only so much food in the freezer. So the microbes will eat it till it's gone. And even though you still have a lake there, there's no longer that permafrost carbon source to feed them. And so the lake will sit there and it will slow down on its methane release. But along with carbon coming out of the permafrost, there's also other kinds of nutrients, phosphorus, nitrogen, that stimulate the growth of plants around the lake and in the lake. And so the lake changes roles from a greenhouse gas emitting lake that's causing climate warming to a lake that actually has a net uptake of carbon. Carbon dioxide gets absorbed by the plants, and then those plants die and build up thick peat deposits in the bottoms of the lakes. And these lakes are often deep and anoxic, so decomposition rates are slow in the first place. And then eventually many lakes drain. And when the water goes away, now the sediments refreeze. And so it locks that carbon up in new forming permafrost. And when we look at how many lakes there are in the Arctic and line up all the birth dates of those lakes over time, we can do a mass balance calculation. And what we've determined is that early on in the Holocene, the Arctic lakes were a net source of methane, but I think it was 5,000 years ago, they actually switched. And so even though we have many lakes today that are new, big sources of methane, overall, if we look at all the lakes, they are actually having a net climate cooling impact.
Okay, that's really interesting. Is that increasing, or is that just sort of a background? Is that going to help us, or?
Well, I would say it has helped us over thousands of years. The future, a very interesting thing, if all the models and all of our data are right, then as the Earth came out of the last ice age, over a period of 8,000 years, Earth's climate warmed about 3 degrees Celsius, maybe 4 degrees Celsius. That same magnitude of warming is expected to occur in the next 80 years. So the magnitude of warming is the same, but the rate of warming is very different, 8,000 years instead of 80 years. And the baseline is different. We went from colder to where we are now, and now 3 degrees warmer. So all this carbon that the lakes have been soaking up and storing in the bottoms of lakes and then refreezing when the lakes drain into peat, that will be vulnerable to thawing and decomposition in a warmer climate. So that mechanism that's been helping us with climate cooling for a long time in the past is not something we can count on in the future with such rapid warming and warming to such a degree that widespread permafrost thaw is actually going to release all the carbon that's been sequestered.
Especially if it starts to burn.
And right, or if it starts to burn, that's right. But I mean, some of these peat deposits are very thick, meters and meters thick, and I don't know how deep the wildfires can burn into peat. But either way, burning will accelerate it even more because it's disturbing that surface oil and causing any ground ice to melt beneath.